So we're just about to start the session, so I will kick off. I was just waiting for as many people to join as possible. So thank you everyone for joining the latest WA Data Science Innovation Hub webinar. Today we have 4 fantastic presenters talking around energy analytics, so how they're using data in the energy sector. So just a little bit of housekeeping before we get started. There is a Q&A button, so you should be able to see it down the bottom of your screen. So please do send your questions for the presenters throughout. We will leave the Q&A till the end though, so the Q&A is open, so please feel free to send them. We'll moderate them as we go. If you could just let us know who the question is for, so which presenter, or if it's to all presenters, that would be ideal, and then at the end I'll be able to direct it to the presenter. So just before we get started, I thought I would just give those of you that don't know what the WA Data Science Innovation Hub does, just a quick little rundown. So we have been up and running now for about 18 months. And this is really sort of our vision and mission and what we hope to achieve for WA. So it is a state government initiative and funded by Curtin University as well. So really what we're aiming to do is it's all around diversifying the economy and building jobs essentially through data science. So how can we accelerate the uptake of data science within industry across Western Australia? We do have a website. It's got quite a lot of information on there, so I do encourage people to check out the website. We have regular newsletters, blogs, information coming out, so you can join the network and you'll get information around what the hub is doing. So a big focus on upskilling. We do have a upskilling boot camp coming up, and we'll continue to roll out those boot camps over the next 12 months. So without further ado, we will get straight into the webinar. So I would like to firstly introduce our first 2 speakers, Russell and Anton, who are from Ecocentric Energy. So Ecocentric is a Perth-based organisation that's developed next generation data acquisition technology combined with advanced machine learning to service the energy sector. Russell Wilson is the director and co-founder of Ecocentric Energy, and he's held several positions including project management, senior estimator, as well as consulting and technical advisory roles for numerous large electrical contractors in Perth. And he has over 2 decades of experience in sustainable power generation. Anton is the CTO at Ecocentric Energy and has a background in technical background training as an electronic engineer. He also has an in-depth knowledge of software systems, in particular cloud-based and mobile software technology. Anton has 20 years experience in creating and operating businesses around technology. So Russell and Anton today will demonstrate the Ecocentric Energy Newman's Analytics platform and show us essentially how that platform can be used to explore the barriers to unlocking the value of energy data in WA. So I will now hand over to Russell, who will kick off. And as I said, please let your questions, bring your questions in as people are presenting, and we'll hold them to the end. Over to you, Russ. Thanks.
Okay. Rightio. Okay. I believe we go. So thanks again for having this show on WADIG. It's great to be on here. I'll tell you a little bit about Ecocentric. Ecocentric Energy was formed back in about 2006, and we worked with solutions and products around energy efficiency, and a large part of our work was around energy auditing. We would go to site and have a look at all the loads and trying to work out where the energy was being consumed and how we're going to go about providing solutions and insights to the clients on how they can improve on things. But what we found out fairly quickly was that the biggest barrier to the acceptance of our proposals and us getting work was the lack of good quality energy data. You could get your energy bills from your meter, you could get your interval data from Western Power. You could see quite a bit from that, but it was always half hourly. It was never granular enough, and we could never really be sure what was consuming the power. A whole site is a whole site. It doesn't break down into individual circuits or individual bits and pieces of plant. So without spending an inordinate amount of time gathering data, we thought it would be best to try and find ways of measuring the branches, the actual circuits, the individual devices themselves with metering. Wasn't a lot on the market. We found a branch circuit monitor and tried that out and a few other things, and then we realised that there's a real chance to build something that would fit that niche, and that's where Newman came into it. So the product really came down to measuring every single circuit on a switchboard. That was around about 2012 that concept came up, and in 2015 we started kicking off patenting and building Newman, and now here we are. Next slide. Now everyone knows that data is valued. It's I'm not going to belabor the point. We see where it's going to end up, and I think we all agree with that. It really does increase the value of a business if they get the digital transformation side right. And I think the companies that don't transform are going to be left behind, and they recognise this too. If you look at this graph here and you see the manufacturing section there, it's the largest one out of all of them. That kind of surprised us when we saw that, because you imagine oil and gas and retail and all that sort of stuff being more highly prized, but manufacturing is such a fine line. They save a little bit of energy, they make some money. So they're always constantly upgrading and transforming their technologies to keep a pace and to keep a cutting edge and beat their competitors. That's a bit of the finding we got there. Yeah, digital transformation is the key word there. If we can be part of the transformation, then all the data analytics that we work on can find a market, and it'll pull us into the future. We'll talk about the barriers of that later on, and there's a few of them. But Newman hardware, as it says there, it's a bit of an edge device that captures data on individual circuits. And we can, through our system, look at the fingerprint of an individual device based on the way we see it at the switchboard. So we're measuring energy from the switchboard of all the devices in a building, sending the data into the cloud, and that's our big data. You notice down the bottom there, better data makes business more productive, safer, faster, and fitter. The safer part of it comes into our detection of arcs and potential fires, etc. We can all agree that the digital transformation is accelerating. There's a lot of information there. I'll draw your attention to the last paragraph on this slide. Globally, electric motors consume about 9,000 terawatt hours per year. And if we can improve them slightly, then we would save an awful lot of energy, because it's such a large percentage of the world's energy is consumed by motors, approximately 45%, I've read. I'm going to talk about motors a bit later on, and this is why I'm talking about motors, because it represents such a large chunk of our consumption. How our tech works. I won't go into too much detail here, but you can see from that graph there, it's a slipping fan belt on an air conditioner in a data center. The air conditioner was playing up. No one knew that was happening. All the other air conditioners in the data center were compensating for it. And just by a routine inspection, one of the mechanical engineers came on site and he noticed the slipping fan belt, repaired it, and was back to normal. So you can see the down the far right-hand side of that graph there, the normal line is above that purple one there, and the abnormals are the rest of it. So really, it was just by chance this particular fault turned up just the day we installed it. We don't know how long it was slipping for, but basically the company that has this in loved it and thought this is great. So by knowing what happens and isolating anomalies, we can then alert the key personnel on a site to what potential problems they're going to be. Then it fits into the preventative maintenance category. So these are the key elements of the Newman system. On the left there, you can see the red, yellow and blue and black lines. That represents the power lines into a building, 3 phases of neutral. The blue items that clip around the cables are called current transformers, and they detect the amperage of the current flow. They're designed by us and have a few nifty little designs in there for electricians, ease of installation, etc. The Newman collector then takes the voltage references and the current references, and through those two measurements, those two parameters, we can see an awful lot of data, mostly because of our sampling rate, and which we'll get onto a bit later on. But the high frequency data is then meshed together, so we can see a whole building if we need to, using gateways and so on, and then to the cloud from there, where we can process the data. There is some processing done down at the collector level, so that the huge amounts of data are then useful later on. So there's quite a bit of processing done there. Each collector has the processing power of 3 high-end laptops, if you like, and 1,200 component parts per unit. So they're pretty complex. They're not just a meter; they are a much more complex device than that. Now, talking about complexity, you can put a graph like this on a page and talk about a sine wave for electricity. It's pretty simple. 50 cycles per second is typically what we run our voltages on here, and our power on in WA, in Australia, and most around the world, except for America, of course. They have to be different. They're on 60. But if you start to look deeper into it and sample it minimum 8,000 times a second, which is what Newman does, you can add some features to that seemingly simple sine wave. This kind of information is what we're talking about here. Energy data is complex. There's a lot of different things to look at, and by understanding this and processing this fine detail, we can unveil an awful lot of stuff. I'll give one example. If you look at a simple domestic fridge, for example, it's got a freezer door and a fridge door, and there's a light in each cubicle. The compressor might be running, it might not be running. The fridge door might be open or it might be closed. If you've got a combination of 3 or 4 different things, and maybe an ice machine or a chilled water, etc., you've got one very simple machine, but there's a lot going on. But with this data, you can see when the fridge door is open, because the light comes on and it shows a different pattern. You can now put a request in, or a notification, an alert. How many times does the fridge door open, for example? That's one of the things. It's just a simple example. So in a complex production line and in industry, you might look at conveyors, solenoids, motors, etc., and start to break it down into the component parts. A good way of sort of looking at this is the old water analogy. I love water analogies. For those who are not familiar with electrical data and so on, each device is like a rock that dropped into water creates ripples. They go in all directions, upstream from the switchboard or upstream from the motor where the load is on, out into the street. They're noisy things. Now, when you get multiple loads, you get multiple ripples. And you can see on this example here, where they overlap, there's sort of an increase in amplitude or complexity around it. With the speed of analytics now and the help with our good friends over in CSIRO, we're starting to sample these waves, these wavelets, and many people around the world are sort of looking at this untapped source of data, especially in Spain. For some reasons, a lot of good analytics coming out of Spain around power quality, around wavelets. Even in Europe, they're talking about a wave capture. In US, there's a whole groups of people who specialise in power quality analytics. I think that's probably a good snapshot of Ecocentric and Newman and the product. I'll hand you over to Anton now, and he can get a bit more technical about or showing you the dashboard and how we represent the data. I'll come back a bit later on and just go through the motors and some barriers around unlocking the value of data.
Great, thanks, Russ.
Nice.
I think I'll just share my screen here as well. Share that one. So hopefully everybody can see that screen.
Yep.
Okay, so Russ has given you a little bit of a rundown on the Newman system itself and how it works and how we actually get the data. As he said, we sort of set out to create our own custom hardware platform to do the data acquisition, and the reason for this is because, as we all know, that the quality of the data that we work from is really very, very important for the results that we want to generate at the end of the day. So we created our own data acquisition system that allows us to easily install and deploy the hardware in various buildings and connect it to various devices and get a large and a rich quantity of data, volume of data that we can work from. What we then do with the data, as Russ mentioned as well, is we process some of the data on the edge device or on the collector. We do some feature extraction out of the data. We do some frequency analysis and spectrum analysis on the data as well to really generate a really rich set of information. And the purpose for that is twofold, really. And our purpose as a business has always been around helping people to save energy and being more efficient with the energy that they use, but also to add value on a maybe a more economic benefit and help people to maintain their devices and their electrical devices better and understand their electrical devices better, in essentially to save them money in their overall cost of ownership of these devices. So once we've gathered the information, we typically send a lot of this information into the cloud where it gets stored and curated. And it's not only the electrical data or the time-based data, it's also a rich set of metadata that we record about where these devices are, where they are operating, longitude, latitude, so that we can overlay weather data, meteorological data, and so forth, so that we have a rich set of data that we can use to produce outcomes from. So what you see on your screen is essentially the dashboard or the first page of our web interface. And the first page of this is really designed to help building owners and owners of devices understand their consumption and their usage from a cost perspective and from an electricity bill perspective. So here we use our data, for instance, to create some forecasting. What we're looking at here are two fast food restaurants. Comparing one to another over a month. And as you can see currently with things opening up again with COVID-19 and so on, that the electricity consumption is trending upwards for these guys. So you can see that their electricity bill this month is forecast to be about 12% higher than what it was last month. We also give them detailed information, essentially day to day, how it's going. And we also look at things like max demand, because that also affects the electricity bill at the end of the day. So this is just an example of how we use the data to give them real actionable insights and to help them to save energy. Another great tool for them is the ability to compare the various things in their restaurants. So here you can see we're looking at air conditioning and we're looking at refrigeration, some of their larger consuming devices. And we can relate these things in terms of cost, in terms of kilowatt hours, and so forth, and compare them to one another to see how they are performing. The next stage of the evolution of our business really is to use this data that we got and to use it as a source for machine learning and for more intelligent analysis on the electrical devices. And the purpose of that is to really create a non-intrusive way of monitoring electrical devices. And with non-intrusive, I mean we simply click those current transformers around the supply cable, and by only having those sensors, not having any vibration or any other sensors on electrical devices, we are looking to determine the state and the operating conditions of these devices, to be able to predict faults and predict things going wrong, and also to monitor the device as it operates, to look at the various operating modes and the states that it operates in. So I'll give you an example of some testing we did in our lab with a pump. So this is a water pump where we have an inlet valve that we can open and close as we wish, and we can close it to certain percentages. So what we do is we typically run the pump, and we've got the valve open at 100%, and then we gradually close the valve down to 75%, and then we close the valve down to 50%, and we close the valve down to 25%, which then essentially creates a cavitating state for this pump. So the pump is in a cavitation state there. And then we switch the pump off again. So here you can see in time series, the blue line there is the power consumption of the pump as it goes down. The green line is the power factor, and the red line is the reactive power. So you can see how the reactive power is essentially staying constant. And then the real power goes down as the pump starts cavitating, which then affects the power factor. So these are fairly simple features that we extract out of the electrical signal. We also extract a lot of information around the frequency spectrum, which I'll show you in a second as well. What we can then do with this data, once we have it in our system, we've got some machine learning algorithms integrated, and this is an evolving part of our business where we're adding more and more different types of algorithms that we can use. But we can then go and look at this data in a slightly different view. This is essentially a histogram showing buckets of the various parameters. Now, if we look at this in a 2D scatter plot, it starts to become interesting, and we can see how the how clustering algorithm would potentially start to identify clusters. So what you can see here is down below is the device off, and then here you can see slightly darkened dot is one of the operating states, another one of the operating states, and another one of the operating states, with the dots in between representing essentially the transient state as it moves from one to the other. So this is looking at power factor. This is looking at kilowatts. Now it gets quite interesting if we put this into 3D. We can have a look at the clusters effectively in 3D space, and what the algorithm is able to do, it's able to identify these clusters and then model this data, and then we can use that model to, going forward, predict what state the device is in. So by learning and training the model, we can then use that model to predict, and we can then use that to set up notifications and alerts based on all of the data that we've got, including the states of the device that was essentially detected by the algorithm. I can just show you some of the research work that we've done here. Here you can clearly see when we have trained the model on, and we're using more than just the 3 parameters. We're using, let's say, 1, 2, 3, 4, 5, 6 or 7 of the features that we extract out of the electrical signal, including the 3rd and the 5th harmonic. The prediction model becomes really effective. So you can see where it's green, it's essentially off, and then when it's blue, it's cavitating. So it's really detecting that fault condition very accurately, and we've got that integrated in our system to then be able to alert on the basis of that and notify third-party systems, or notify by text message or by email a maintenance engineer to go and have a look at a certain device. So this is just an example of how we can use data through machine learning algorithms and through our visualization platform here to detect specific things happening with devices. Now, a very common thing is really just the difference between normal and abnormal, and this is what we refer to as fault prediction, where we would model a device in its normal operating state, and if any of the parameters or combinations of parameters move out of that normal operating state, we would then say that it's in an abnormal state, and we would then alert people to that. So this is just a quick overview. There's obviously a lot more detail that we can go into, but I just wanted to give you a rough idea of how we typically use the data through machine learning algorithms to create some valuable customer side or user side insights and actions that they can then use to essentially operate their devices in a more efficient and a more intelligent way. So back to you, Russ.
Okay, thanks, Anton. That's great. I'll just get my PowerPoint up again. Here we go. Right, now just talk about barriers to unlocking value in energy data. It's no different to any other data, I suppose. The value in energy or any data is really in what the outcomes are, what the output is. The biggest barrier that I've been finding over the last 5 years around energy data is ourselves, people. You know, people have fears, etc., around artificial intelligence and all that sort of stuff, and also just the sort of costs and complexities of getting data in. And the biggest barrier, I suppose, to really to unlock the value is what's in it for me, they say, the industry and people. There's a kind of a societal barrier around things. Ignorance is bliss. We want answers, not questions. We like what we're familiar with, and we fear of being manipulated. There's a lot of that going on. It's not exactly fun for people who are not into it. If you're looking at data and graphs and you're that sort of person, then you find it interesting. But I guess gamifying data is going to be something that would really help and make it a little bit more fun. And I mentioned the fear of artificial intelligence there. On the industry barriers, engineers, and I've presented engineers quite a few times with voltage optimization and power factor correction and harmonic filters and all sorts of technologies. They understand how they work and what they're all about. But they're also very conservative in a way. They can't afford to get things wrong. They can't afford to recommend a solution based on data unless they're absolutely sure that their bums are covered. They have this sort of intrinsic reticence to try new things, and that's kind of good, because you need that. Not everyone's a risk taker, but that's a big barrier, is that to get them to change, they want to see it being done already. They don't want to act on false positives and get themselves into hot water. In industry, people have an existing business model that works. They do fear upsetting it by trying new things. That's a big barrier to the unlocking the value of energy data. There's a whole pushback against spending to save on energy. You can look at solar, for instance. If you invest in solar and the payback period's 5 years, people will going, well, it's cheaper just to put up with the inefficiencies of what we've got at the moment. So that change is very slow. I've had people saying, I'm not an energy manager. I'm not here to look after the energy management stuff. So it's not my job. That kind of approach is a bit of a barrier. We've all got a lot to do, and by giving lots of data, we're actually creating questions. As soon as you get more insight into what's going on with good quality data, the questions come thick and fast. And that is a real issue for a lot of people, because they feel busy enough doing what they've got to do right now without adding more to it. Unlocking the value of energy data, and I chose electric motors because 45% of the world's electricity is consumed by electric motors. So it's a good example of how do we unlock the data. And Anton described just recently there about the cavitating rotor on a pump. It's a great example. There's slipping fan belts, there's worn bearings, there's all sorts of causes that make electric motors fail. Running through those items on the side there, Watercorp is the highest single user of electricity in Western Australia. That's what I've been told. Critical infrastructure rely on motors to perform. So you can imagine hospitals and chillers and freezers and samples and all sorts of stuff that relies on motors, air conditioning and so on. Motors are 99% efficient. They really are quite efficient. And I go back to my earlier slide where it talks about how much the world could save by improving efficiency of motors. There's not a lot you can do to something that's really quite good, and there is always room for improvement, but it's all about the load. It's all about what supply, what power goes into a motor and what comes out the other end. So the things that cause motors to fail are typically overloading. So, 30% on this graph here, you can look at a nameplate on a motor and it'll tell you exactly what it wants from the supply in volts and frequency and so on. And it'll tell you what it'll give you in RPM on the output. They don't vary unless you vary them yourself. If the supply going into it, if the voltage fluctuates up and down, you can have issues. For instance, if it's designed to operate on 240 volts, well, they're mostly 230 volts, but you give it 250 volts, there's 20 volts of pressure there for it to deal with, so it goes off in excess heat. So now the windings are running hotter and they'll burn out the motor. Then the load.
Russ, I'm sorry to interrupt you. We are going to have to start moving on a little bit.
Okay.
Just for time, sorry.
Oh, that's good. I'm just about done. So, yep, that's where we are with that one. This is the first motor that was built back in 1832. They've come a long way since then, and you can see how efficient they are. It's an example of where we're going with data. It starts rough and it ends up pretty flash. So I think that's where we're heading. So thanks very much for your time.
That's great, thank you. And I can see your passion, both you and Anton. So I imagine you could talk about this for hours and hours. We do have a few questions coming through, but like I said, we will leave those to the end and we will move straight on to our next speaker, who is Dr. Anna Hayes. Anna is the Principal Management Consultant Statistician at Data Analysis Australia. They have a rich history working with utilities industry, in particular the electricity industry, with a focus on providing insights and usable models to enable strategic business decisions. In this talk, Anna will discuss two such projects, one being the residential customer segmentation and load profiling, and understanding optimal PV and battery sizes and combinations on a large scale to manage system load profile. So Anna, I will hand straight over to you.
Hello, thank you for that, Liz. Hope that everybody can hear me. Can you hear me now?
Yep,
okay, excellent, thank you. Thank you also for the promotion to doctor. I'm not actually a doctor, I have only honours qualifications, but that's very nice to be considered like that.
Sorry.
I better be honest before I start the presentation.
Very good. Okay, doctor, over to you.
My presentation. So as mentioned, I work at Data Analysis Australia. So we provided statistical expertise as a leading analytics consultancy since 1988. So had a big 30th year celebration a couple of years ago. For a small business based just in WA, I think that's pretty impressive. So just some of the businesses we've worked for, organisations we've worked for in this particular industry are listed on the slide there, but we've worked for many other clients in the industry as well. So a little bit about who we are for those of you who haven't heard of us. So we're a speciality data science statistical consultancy firm, very much with our roots from the statistical side. So we're established in 1988. We are based in Perth. We're only operating from Perth, or from Nedlands near UWA. So we consult in a variety of industries and application areas for government and business. So energy is just one of our many areas that we work in. And we have a very mixed team, very experienced consultants, more than 20 years, all the way through to graduate consultants, qualified in a number of quantitative disciplines. And we work collaboratively with clients to use data to provide insightful business solutions. That's just what we try and do on all of our projects. Seems quite appropriate to this particular webinar topic as well. So I won't talk too much about energy data because I think we all listening to this know it, but I will say very briefly, it's very rich, it's very diverse, and it's very valuable, as has already been said. The more data you get as well, the more questions that can be asked, the more insights, it just becomes a big circle. But there are some definite challenges within the data as well. So I'm going to list a few of them, then go through a couple of case studies, and then just a quick wrap up into some of our approaches to dealing with the challenges. So some of the common challenges are integrating across multiple disparate data sources and collection technologies. Missing data, in particular time series data, if you've got half hourly or hourly or minute or monthly or daily data, and how to align time series across data sets if they are measured in different levels of frequency. Inconsistent coding and nomenclature between data sets you're needing to analyse together. Separating data collection anomalies from real data collection signals if there's errors, or signals that something's actually happening as opposed to an error in a reading. Working with different platforms and tools effectively and efficiently, and data that changes. You have one-off snapshots, you have regularly updated snapshots that don't always match what they should match from previous versions, and then you have real-time data as well. Sorry, there we go, page down. So first case study I want to talk about is customer segmentation via load profiling. So essentially we wanted to understand typical electricity consumption patterns of residential customers. So this was to enable the analysis of impacts of different pricing regimes, contributions of different types of customers to system peak, which can hence assist with strategies, and to assess effects of potential changes in consumer behaviour. So the data we had available for this project was a large set of 30-minute observations for each customer's usage over a number of years. It wasn't exactly the same number of years for each customer. We had greater than 10,000 customers, which means hundreds of millions of cells, millions of records. And the desired outcome from that is a small handful of meaningful data profiles. I've got a couple more slides, but you can see our outcome there already. So our approach to this, first we wanted to remove some of the noise, as we call it as statisticians, or random variation, and also reduce the size of the data. This is a project from a few years ago, I'll say, so the computer power was not as good as it is now. But reducing data is always an important element anyway to a big data problem. So essentially we first averaged the data by time of day, weekday versus weekend, and different times of year, because we knew that they were the important differences in most customers' usage. Then we applied statistical clustering methods to group customers with similar usage patterns, and we did some further averaging and analysis and some visual display, which enabled us to reduce the clusters to 4 different types of residential customer. So we had a lot of experience in the energy industry, so we applied the background knowledge and our understanding to make sense of the profiles. So these are the 4 profiles you can see. The green one there essentially is solar panels, low usage during the day. The red one is air conditioning, pretty much used all day long. This is in particular in some of the hotter areas within Australia where aircon is just on all day, every day, especially during summer. So you can see that that red line just constantly increases. There's a profile which essentially sort of indicated air conditioning is used only in the mornings and evenings, bigger peaks in the morning and evenings, but a bit of a drop off during the day. And then a 4th profile, which was essentially no air conditioning. So still had bigger peaks morning and evenings, general breakfast and dinner time and evening time activities, but no aircon to be bumping that up. So again, that's really important that not only did we come up with 4 profiles, but could come up with some good descriptions that are meaningful. So the simple averaging process gets us this far, but then we wanted to actually go to enable decisions to be made. So we fitted some sophisticated statistical models to the raw half-hourly usage data for each customer, taking into account, amongst other things, their assigned profile, so whatever profile they're assigned to based on the aforementioned clustering, the daily weather conditions. We brought in weather data from around the country and where the houses were situated on a daily basis, and different flags for whether it was a weekend or a weekday or public holiday, and various other elements that we know impact on energy use. So what this modelling enabled us to do was then further answer further business questions such as how much power is likely to be used at any given time of day on any given day of the year, what would a typical profile look like for a typical weather year, and how might overall profiles be affected by an increase in, say, solar take-up rates, which would shift some customers from their existing profile being, say, a blue line onto the green line profile. So case study 2 now is analysing PV and battery usage. So essentially a totally different business question now, with the aim being to understand optimal PV and battery sizes and also combinations of PV and battery sizes, but on a large scale to manage system load profile. So looking at this, if suddenly batteries become affordable, what's going to be the impact on the network providers who are going to have to supply the overall remaining or residual power needs. So lots is known on the large scale uptakes of solar power, but less so on the battery uptake on a large scale, where customers will suddenly be able to generate their own electricity supply at night time as well as during the day. So our approach to this was we developed a bespoke simulation processor incorporating models, so statistical models for the amount of usable electricity generated by solar panels, the likely usage of a storage battery, and the total amount of electricity needed by a customer. This approach meant that not only could we change the input values, such as the size of solar panels, but also the assumptions behind the models, and hence could investigate numerous different scenarios and consumer behaviours. So modelling the solar panel generation is relatively straightforward. It involved calculations of the angle between the solar panels and the incoming sunlight. And our simulations here involve the time of day, season and panel angle to calculate the electricity generation for an entire year based on a per kilowatt basis of installed solar panel at different locations around Western Australia. Obviously, you know, some places say north of Australia, you would generate more from the same 1 kilowatt panel than you would some places south. Modelling the batteries was somewhat more complicated and required a lot more sophistication. And we were really keen to investigate and incorporate flexibility because we don't know as much about how people might use them. So for example, not only the battery sizes did we want to incorporate scenarios for, but different ways of using it, such as customers might choose to charge the battery when they've got excess solar supply instead of selling their excess to the grid, or they might want to do both. So they might want to charge their battery and draw from the grid at the same time. They might want to use their battery as soon as their solar powers are insufficient for their current needs, rather than saving the battery and importing from the grid. Or they might want to say, I always want to charge the battery between these hours of the day, and I always want to use the battery between these other hours of the day. And many other scenarios. And we also wanted to consider what's an optimal battery usage or like a control for a system level so that we don't get the same issues with solar power. But if, you know, for example, if it could be optimized from a system level as opposed to a customer level, how that might impact. The battery model also had to include physical constraints such as maximum charge and discharge rates. And because it charges and discharges all the time, we had to incorporate sequential modelling from hour to hour. It became quite a big project and we learned quite a lot about batteries in this process. So the graphic here shows a hypothetical customer's power on a typical summer day based on just one of the scenarios. Essentially, the green lines there in the early morning and the evenings, that's showing what the customer's drawing from the grid. The yellow is the power that they're generating and using themselves from solar, and the blue is what they're using from battery, from their battery. So we had a lot of different graphs that looked very different to this, but it gave really good insights into the types of outcomes different behaviours could show, as well as different battery sizes. So we ran tens of thousands of scenarios using an automated process, of course, to investigate the effect of combining solar panels and batteries of various sizes and with different battery charging and discharging rules for every hour of the year. Obviously, this required efficient algorithms and parallel computing. But it also allowed aggregation to understand potential impacts on the total system level as well as for the customer. So really, you know, could provide a lot of insight. As a final step to this, well, final step to the part of it I'm talking about at least, obviously costs are also important. The bigger PV system you have and the bigger battery, of course, the better it would be in many ways, but costs become prohibitive. So part of our analysis to really understand what might be reasonable outcome was to calculate costs for each customer for each scenario as well. Those costs incorporated direct costs of purchase, but also maintenance, saving on future energy bills, etc., in order to come up with combinations that may be appropriate and attractive for consumers. We then displayed these. Again, have to then display your results in a way that's meaningful in a heat map, with red being the lowest cost combinations through to pale yellow being the most costly. And the 2 dimensions shown here are the battery size, so the kilowatt hour battery, and the solar panel size going up vertically. So the outcomes of this particular case study were a range of cost-effective combinations of solar panels and batteries for consumers being determined, providing an understanding of the variation that might be seen in the long-term customer behaviours. It's really important to understand what might happen, but also the variation in what might happen in order to get a true picture to make good business decisions on. Really critically for the client with this is that it enabled analysis on likely network effects and risk management strategies. And of course, knowing what customers might do can also help in marketing and other sort of customer engagement and customer education activities as well. So just to wrap up now, that's the end of the 2 case studies I'm talking about. I say 2 of very many that we've worked on. But hopefully through those case studies, you see and also know from your own work, the value of having experienced data experts in working with this energy data. It's, a very challenging source. Oh, I think I just lost my screen. Did I? No, sorry. So energy data is rich with a vast array of fascinating insights, but we have to be very careful and very clever in how we deal with it to really get the true value. So, we do this by being very detailed, focused, and fastidious when it comes to the data. We know what sort of errors to look for and how to look for them. Is quite crucial. You don't necessarily have to fix all errors, but at least be aware of them to get a good, meaningful outcome. We're careful, robust, and reproducible with our coding. We want to make sure we can repeat the same work with the same data and the same code and have the same answers result. And also, if the coding needs to change, the reasons for this are captured. And if the data needs to change, we know that it's only an element of new data that is causing changes to outcomes. We also map and model the data from end to end, so from collection through to the analytics stage, to ensure consistent coding of data for the purposes of answering questions for the client. So we really understand the data and try and really work with our clients to understand the data from all elements right through to the end. And if they're taking further analytical work on from us once we've finished our component, to ensure that we've discussed that with them and that our outputs are relevant for their ongoing needs. We also use the right analysis methods for the data, so including but not limited to the incorporation of appropriate and sometimes sophisticated statistical techniques. We typically incorporate and look for bespoke solutions, avoiding black box solutions where possible, but within this taking advantage of previous learnings, automated coding, and data analytic technologies. We work in teams as well, learning from each other and taking advantage of different skill sets and different experiences in this industry and others. And also we think to give the best insights to clients, you need to foster a collaborative and long-term approach to working with the clients. That's the end. Thank you very much. I hope that there was something interesting and exciting in there. Very happy to talk to anybody after this about anything related.
Thanks so much, Anna. That was great. I just want to make a quick note. We are running a little bit behind. If people do need to jump off the webinar, that's fine. We are recording it, so we will send out the recording because we do have some questions as well at the end. But I will introduce James Bangay, who's the Head of Digital Strategy at the Centre of Excellence at NZN Australia. And James will be talking around rethinking the energy value chain with big data and analytics. So James, over to you.
Thank you. Just to check that my screen is sharing.
I might just get Anna to stop sharing and then James, you can start sharing.
Has that worked?
Yeah, yours is stop sharing, and now James, you can start sharing.
Okay. Confirmation that you can see the screen?
Not yet.
Well, those practice runs didn't help us, did they? Share desktop.
Great, got it.
Excellent. All right, well, I want to take a slightly different picture. We've sort of zoomed right down into how monitoring high resolution frequencies on the line can help. And we've looked at solar and the difference it's making in energy profiling. I want to take a step back and look at the macro environment of the energy sector at the moment. And probably in the next 5 minutes, I'll have enough time to whet your appetite to what I think is happening in the world, and we'll watch this in slow motion over the next 10 to 15 years. But if we think about what the infrastructure is that delivers energy, we're transitioning from one very complex environment of the electrical grid that in itself is sustainable to another future complex environment that has many participants, many sources of energy. What's that transformation going to look like? The current infrastructure world, or public infrastructure around the world, is estimated to cost around $50 trillion. If we look at the cost of maintaining that infrastructure on a annual basis, about 5% of that is maintenance, and 10% of that cost is inspection. So we're spending 0.5% of $50 trillion a year on inspecting assets. That's a $250 billion sum inspecting the legacy infrastructure that is being replaced and integrated with the emerging new economy of energy. But what are we seeing as we look around the energy sector today? Very poor interaction of energy with other infrastructures. So the Sydney Light Rail, nearly $500 million blowout because largely of the discovery of electrical assets where they were building the light rail that no one knew about. In that same situation, almost a death as a result of an electrical shock. This is a photo from South Australia, and these are very common. You'll search them on the web, photos in front of garages. The simultaneous build of houses and power infrastructure is very poorly planned. So how do we improve this world and take advantage of digital? We see this emerging world of reconnaissance, where today energy utilities and infrastructure utilities generally run off the transactions that come out of their enterprise. They look at their enterprise resource planning systems or their maintenance systems, and they manage their assets from that. We now see, through the emergence of everything from daily updates from satellites, drones, smartphones that can take 100 megapixel photographs, ground penetrating radar, these sources of reconnaissance data far exceed what we ever hoped to inspect in the field. And over the next 10 to 15 years, we see a transition from the human assessment of condition in field to the deployment of sensors to gather content about the world, and then ultimately the embedding of live sensors. But some of those sensors will never be live. It's not necessarily affordable to put a rot detection sensor in every pole across the country. So there will be this cyclic inspection through reconnaissance. But the number of platforms that are doing this reconnaissance for us are increasing. So autonomous vehicles, for instance, will become part of the reconnaissance platform of infrastructure. Every car that drives down the road in 10 years' time is likely to have some form of video surveillance capability on it that will be looking at power infrastructure, pillars and pad mounts and road curbs, center line markings on roads, all of the things that need to be maintained by people. So one of the things we're developing within NZen is the brokering solution for all of that content from multiple sources to be able to be conflated into digital analytics for infrastructure companies. And we've seen this happen in the agronomy world. agriculture, but now we're seeing it move into these other infrastructures. So I'll jump through a few of these and just talk perhaps briefly about the fact that agriculture overlaps with power infrastructure considerably. In the 5 years just before I left Energy Queensland in 2010, there had been the rate of 1 plane a month coming into contact with power lines. So these are crop dusters and the like, not drones. But just to be clear, 1 aeroplane per month hitting a power line, because that infrastructure is not known, it's not mapped, it's not visible. Planes are flying all over regional Queensland, nearly 1 million square kilometres, 1.7 million square kilometres of territory. How do we get better integration of the infrastructure we're building with the rest of the world? And we see the opportunity of digital reconnaissance as transforming the way people manage that infrastructure. So these are some snapshots that illustrate one source of data. This is LiDAR, laser scanning of power infrastructure. Western Power has done this across their territory. And the things that we can see within this data replace some of the inspections that have been done in Western Power for decades in other ways. I'll jump to a particular view of this and summarize from here. So what we can see through digital reconnaissance as opposed to in-field inspection is the state of every asset. What we normally discover when we do traditional inspections, so that 0.5% of the replacement cost of infrastructure that is being spent on inspection today is only finding defects. It's very rarely finding the state of every asset. Whereas when you send out a sensor or some kind of digital deployment, you inspect everything. And so you can build a complete profile of the asset base. So here we're seeing in blue, for example, the 11,000 volt transmission line or distribution line and the ground clearance. And we see that at 6 meters, about 1% of the asset is at that height. So now we begin to understand the assets that may be considered a defect, those less than 6 meters. These assets could cause an environmental or human danger situation. By being able to identify that 1% or actually 5% of assets that are in that situation, we can then build risk profiles and deploy corrective action against just the assets in that category. But to do that without knowledge of the rest of the distribution can lead to false assumptions about what actually is the threshold for a defect. So depending on the accuracy that we measure, if we measured just 100 mil error, so instead of 6 meters, we had 6.1 meter or 5.9 meter, another 25% of the defect list is increased. So adding an extra 100 mil to the clearance threshold introduces 25% more corrective work. If the corrective work for a typical utility is around $100 million, which is what it is in Australia, then we're looking at another $25 million worth of correction work if that threshold is uncertain by 0.1 of a meter. So we need to understand the quality of the data that's coming from reconnaissance in order for us to adequately build risk profiles on assets. And this will be one of the greatest challenges in the transition to digital asset management, is being able to assess the quality of the inputs that are being used for your asset inspection replacement programs that you'll use technology for. So I think I'll leave it at that and invite people who may have further questions to ask on the channel there, and I'm happy to talk after the presentation as well.
Fantastic, thanks very much, James, and we will make your details available in case anyone has any direct questions for you, because I am conscious of time, but we do have a number of questions that are coming through, so I will ask a few of these. I'll probably run it for the next 5 minutes, and then we'll look to jump off, because I indeed have another meeting to go to myself. So so I guess firstly, just to frame the issue, and for any of you presenters that know, how much electricity do we actually produce or can produce in WA, and how much do we use or need in the next decade? So I'm not sure. I mean, James, do you sort of have a sense of that, or any of the presenters? No, too hard. Okay. We will look into that and get back to everyone on that one, because if you guys don't know, then I definitely don't know.
It's probably just an interesting piece to put in there, though, that certainly in Queensland, and I believe it's the case sometimes in WA, more energy is being produced by solar on people's roofs than can be consumed by any load at that time. Yes. So we now, for the first time, are in the problem that we can't send the energy anywhere, and we're almost paying people to turn on some form of consumption to draw energy. And this is where the interaction with water obviously will be a very powerful interplay, because at those moments, Water Corp can turn on their pumps and effectively get energy that would otherwise be being wasted.
Yeah.
And it's also where the battery combination on a large scale, like one of our projects, could very much also come in to take that excess at those times and have it for the now subsequent peaks later in the day.
Yeah, absolutely. So this is probably maybe a question directly to Anton and Russ, and in your, I guess, in particular, your forecast or your predictive modelling, have you factored in the impacts of COVID for your clients in any of that? And even to you, Anna, as well, I guess, when you're currently working with clients and looking at sort of predictive algorithms.
Yeah, well, actually, I can just recently with the City Council in Perth here, one of them, they have their whole infrastructure running, but only 10 or 15% of the people in there, and they wanted to know how much energy they were wasting. So yes, definitely knowing the footprint per person and post-COVID or pre-COVID, it's certainly good data that they want. They're looking for it.
Yeah, interesting.
We don't have any projects at the moment running through that, but we would certainly take that into account for future work on forecasting. And there have been other, I suppose, not quite the same circumstances, but, floods or other major events in towns that we've had to take into account. And in many ways, we would approach it in a similar way in terms of identifying these are the differences that are potentially caused by COVID by the analysis over the history, and then how that might play forward as well, which would be both data driven and also would have to have just some qualitative insights and assumptions built in.
Yeah, and it will be interesting, I guess, in terms of energy usage and people changing work habits and things like that will obviously come into play.
And I mentioned something interesting there about floods and things happening. Part of some of the work that we're doing with water and specifically remote pumping stations and stormwater pumping stations in the UK is about understanding whether those devices are in a good state for when the problem comes, that they can switch on and do what they're supposed to be doing. And looking at doing that through the electrical data is a focus for us with some of our UK clients.
Okay, I'll move on to the next one. So Anton, this is in relation to the machine learning models you built to predict failures. Are these updated? I imagine they are. Obviously, ML models train themselves as well. But how do you update them and using what decision process?
Yeah, that's a good question. We have quite a sophisticated deployment mechanism through our network, which is effectively our hardware, our edge devices that are collecting the data in our cloud infrastructure. So we have the ability to deploy models and updated models across our network whenever is necessary. Typically, some of these are built in conjunction or working together with the client to solve specific problems on specific machines, and we would build the best model we can at a certain point in time and get a certain level of accuracy and certainty around certain faults or fault conditions that they're looking for. If they needed to improve those, then we would typically go through another bit of training process and deploy the models as needed. We have the ability to run models on the edge device, which gives us access to the high frequency, very, very high resolution data, or we can run the algorithms on the lower frequency or the aggregated data in the cloud. And yeah, the technology these days just make it super easy for us to deploy algorithms across the air in a collector that's sitting somewhere in a remote location, no problem.
Yeah, okay. I'll probably just ask a couple more. So this is an interesting question around weather data, and seeing as it's been mentioned a couple of times by speakers, are any of you looking at real-time weather data integration, either through in situ sensors or using BOM weather stations? I know obviously DPIRD has detailed weather data as well. So I might quickly throw to Russ and Anton, then Anna, and then James.
Absolutely, yes. We use a cloud-based service that's currently that's recently been bought over by Apple, actually, to supply us a whole series of meteorological data points. We can essentially specify the longitude and latitude, and then get detailed, I think it's half an hourly, weather data about temperature, humidity, rainfall, wind, etc., which we then incorporate into our database, and we can then use that in combination with the electrical data for setting up quite sophisticated alerting and notification based on that.
Yeah. Anna?
Yes, we actually have a project that sounds quite similar to how Anton just described that, yeah, without going into details, which I can't, but yeah, getting the live data and running it and for an alert system on a very frequent basis.
Yeah, yeah. And James?
Well, I just want to answer, it's probably in a slightly different way. There are official sources of all sorts of data, and weather data, of course, is one of them that come from the bureaus like BOM. But one of the things that we're seeing happen is the proliferation of consumer managed devices and the ability to use those to aggregate and build data in safe ways, because you've got enough redundancy that you can count for the one that's been placed incorrectly in too much sun and so on. And in general, what we're seeing is a massive swing towards consumer generated content instead of corporate generated content. And in energy companies, particularly over the course of the next 10 years, we predict that more data will come from outside the company than generated from within the company.
Yeah, yeah, interesting. Okay, guys, I actually might leave it there. There is a question about data gamification, and Russ, you did mention that, but I'm thinking that might be a good blog piece or something. So I might hit you up on that.
Oh, don't start me! Don't start me.
I might hit you up on that a bit later, and we can post it on the WODSI website, because I was quite fascinated in that those comments you had around that as well. I think it's quite interesting. So I just want to end by thanking you all very much for providing your time and your absolutely fantastic insights this morning. Apologies that we have run over. Like I said, the session is recorded, so you will see. We will post that on our LinkedIn page and the like. So. We very much hope you enjoyed it, and can't thank you presenters enough. It was really fascinating, and we do want to make these sessions quite technical in nature, so I hope that we've achieved that. I feel like we have, and given some people some really good food for thought on how they can use data in energy. So thank you very much, and have a great day.
Thank you.
Thanks.
Bye.
Thank you.